The construction and collapse of the Tacoma Narrows Bridge, 1940. When the Tacoma Narrows Bridge opened on July 1, 1940, it was an engineering marvel, the third longest suspension bridge in the world, renowned for its slender, elegant design. Yet, just 4 months later, it earned the infamous nickname Galloping Gertie before collapsing dramatically into Puget Sound on November 7th. This disaster was a watershed moment that exposed a fundamental blind spot in civil engineering, moving the field away from purely static load analysis and into the complex world of aerodynamics and structural dynamics. The fatal flaw of flexibility. The bridge's failure was rooted in its unprecedented design. In a quest for cost savings and elegance, engineers used shallow, solid plate steel girders instead of the deep, lattice trusses typical of contemporary suspension bridges, like the Golden Gate. This resulted in an extremely high and untested ratio of width to span, 172, and a shallow depth to span, 350. The resulting structure was excessively flexible and lacked the necessary rigidity to dampen movement, allowing it to become highly susceptible to wind forces. The shift to torsional flutter. The collapse was famously, and inaccurately, attributed to simple mechanical resonance. In reality, the failure was caused by aeroelastic flutter, a phenomenon where the alternating force sustaining the motion is generated by the motion itself. The solid plate girders acted like an airfoil. Wind striking the side was forced to separate, creating vortices of low pressure. This initial twisting motion amplified the wind forces in a positive feedback loop, causing the deck to transition from gentle vertical waves to a violent, alternating twisting motion of up to 45 degrees. The final moments and the doggone. The morning of November 7th, winds reached only 42 miles per hour, 68 km/h, a moderate speed. The bridge was closed to traffic after the severe torsional oscillations began. Miraculously, no human lives were lost, as the few drivers abandoned their vehicles and ran to safety. However, the tragedy became famous for the death of a three-legged cocker spaniel named Tubby, the only fatality, who was left trapped in a vehicle and perished when the central span finally tore apart and fell into Puget Sound. A cautionary tale for engineers. The immediate post-mortem, led by a panel of top engineers, refused to blame any one person, concluding that the entire profession shared responsibility for the knowledge gap. The disaster led to the founding of bridge aerodynamics as a distinct field of study. New designs incorporated open wind grates, stiffening trusses, and hydraulic dampers to allow wind to pass through the structure, ensuring that all future long-span bridges, like the modern replacement built in 1950, were structurally incapable of catching the wind. The enduring cinematic legacy. The collapse was captured on film by a local camera shop owner on 16mm Kodachrome. This stunning footage, showing the bridge twisting and tearing itself apart, was duplicated worldwide for newsreels and is still shown to engineering, architecture, and physics students today. It serves as a chilling, cinematic reminder of the consequences of underestimating dynamic forces in design and the critical importance of testing beyond simple static assumptions. Conclusion. The Tacoma Narrows Bridge collapse was a defining tragedy that propelled structural engineering into the modern age. Galloping Gertie taught the world that elegance in design must never come at the expense of understanding nature's invisible, self-amplifying forces. If you enjoyed this deep dive, follow and subscribe the channel for more videos like this.